As you guys know, I want to talk about the graphs of the secant of theta, the cosecant of theta, and the tangent of theta. Now, before we do those graphs, I want to examine the behavior of a function that you may have seen before. And even if you have seen it before, I want to give you this description of a certain aspect of its behavior that will help us when we're examining the graphs of the secant of theta, the cosecant of theta, and the tangent of theta. Okay, and so without further ado, let's discuss this. What function am I talking about? I'm talking about the function f of x equals 1 over x. Okay, and if you guys have ever seen this function before, and I imagine most of you have, but if not, let me just show you here in broad terms what the graph looks like. And I think it's so essential to know what like the basic graphs, what the basic functions graphs look like, because it helps to develop the intuition. Okay, so the graph of the 1 over x looks like this. Okay, as you get close to x equals 0, the f of x grows indefinitely. Okay, or we could say that it goes to infinity. Okay, as x gets very large positive, the 1 over x uh, gets very, very small. Okay, we could say it goes to 0. Okay, or we could say that f of x tends to 0 as x goes up to infinity. Just as we can say that f of x tends to infinity as we approach 0 from the right. Okay, in other words, as the x gets smaller. And in addition, we can see that as we approach 0 from the left, as we let the values of x get closer to 0, but from the negative side, the f of x becomes more and more negative. And so we could say that f of x tends to negative infinity as x goes to 0 from the left. And we can say that as x goes large negative, the f of x goes to 0, but in this case, approaching from negative values. Okay. Now, this kind of behavior, for which we can recognize from rational functions, and this being one of the most simple examples of rational functions, is known as this kind of behavior is described in the form of an asymptote. We say that this is a vertical asymptote because of the behavior I just mentioned. And we say that this is a horizontal asymptote also for the behavior I just mentioned. To be specific, this is a vertical asymptote because as the x approaches infinity, the function grows in an unbounded fashion here and grows in an unbounded fashion here. In this case, this is known as a horizontal asymptote because as x goes off to negative infinity and to positive infinity, the y values approach the horizontal asymptote. Okay, now, for our purposes, in the context of the secant of theta, the cosecant of theta, and the tangent of theta, the behavior that I want to focus on and the behavior that I want you guys to think about is the behavior of 1 over x near 0. We're going to talk about that right now with some numerical evidence so that we can understand exactly why this kind of behavior is seen in this function, and so that I can give you a spotlight into the kind of thinking that I'm going to use when we talk about the secant of theta, the cosecant of theta, and the tangent of theta. And in this particular case, because of the more simple nature of the function, it'll be easier to see here, so that when we transfer it over to those trigonometric functions, um, um, having seen it in this simpler case, it'll be easier to apply it in that more difficult case. Okay. So now what I'm going to do is, I'm going to make a small table, and I want you guys to stick with me here, okay? So let's look at some particular x values, okay? So for example, negative 1 over 10. Oops, maybe not that one. Okay. Let's start with negative. Negative 1 over 10 is fine. Negative 1 over 100. 1 over 100. And 1/10. Now, by the way, you guys might ask, well, David, 0 fits in between, why don't you put 0? And I know that some of you might be aware, well, I imagine all of you are aware that we cannot divide by 0. And so that's why I don't put 0 there. So I know all of you are aware of that, but in case you weren't aware, we're going to just state that explicitly. You cannot divide by 0, right? Now, by the way, on a separate note, just a brief aside, I want you guys to, well, actually, we'll skip that aside, but we'll just continue. We cannot divide by 0, okay? In any case, let's look at these x values. If we were to plot on an xy plane where these x values lie, then we would see that if this is 1, right, then 1/10 is somewhere over here, where we're getting close to the 0 on the x-axis, and 1/100 is much closer to the x-axis, to the y-axis. In other words, 1/10 and 100 are in order as we're approaching 0 coming in from the right. And by the same reasoning, if this is -1 over here, -1/10 is here, and -1/100 is over here somewhere. Now, of course, this is not to scale, right? 1/100 would be much closer to the y-axis, and 1/10 would also be much closer. If we try to slice this into 10 pieces, maybe this is maybe like, but the relative ordering of these is correct, right? So in other words, -1/10 is more to the left than -100. 1/100 is closer to x equals 0 than 1/10, and so on. Now, what is f of 1/10? Or let's start with the negatives. What is f of -1/10? F of -1/10 is 1 divided by -1/10, right? Because our function f takes an input x and outputs 1 over that x. So here, if the input is -1/10, it outputs 1 divided by -1/10. And of course, whenever we divide by a fraction, we multiply by the reciprocal, so we end up with 1 times -10/1. -10/1 is just -10, so we have 1 times -10, that's -10. And if you use that same procedure, here you get -100, here you get +100, and here you get 10. And if you graph that, you can see that here, let's say it's at -1, because 1 over -1 would be -1. Then it's much further down at -10. And here, even further down, obviously it's not to scale, but it's much further down because the -1/100, the f value there was -100. By the same reasoning, you can see that this has this kind of behavior, where here at 1/10, that would be 10 on the y, right? And here at 1/100, that would be 100. And again, that's not to scale, right? But what I want you to see here is this. What I hope you guys see from this is the following pattern. And it's this pattern that is going to help. This pattern is the insight that's going to help us when we're graphing the secant, the cosecant, and the tangent. And that is the following. First of all, I want you to look at this fraction. Let's say I'm going to put as an example in here what it would have looked like if I calculated the f of 1/10. So if I evaluated the function here at 1/10, what I would have gotten is 1 divided by 1/10. And that, of course, equals 1 times the reciprocal of 1/10, which is 10/1, which gave us the 10, right? Because whenever we divide by a fraction, we multiply by the reciprocal, right? Okay. So what I want you guys to see is this. First of all, the numerator of this fraction is 1, right? And I want you guys to remember something. Whenever we divide a positive by another positive, we get a positive number. So that means that as I'm coming this way towards 0, right, I'm dividing a positive, namely 1, by another positive, some small number. And from this table, you can see that as that number at the denominator gets smaller, the fraction gets bigger. And again, because we're coming towards 0 from the right, that number is positive. So we have a positive divided by positive, so the result has to be positive. And since the number on the bottom is getting smaller, following this pattern, you can see that the fraction will get bigger and bigger and bigger. And it doesn't matter how close to zero we get. No matter how close we get to zero, the closer we get, the larger that value is going to be. If we were to divide, for example, something like 1 over 100 million, just for fun, what would the function value be? It would be 100 million, right? Now, of course, this is not really that big of a number. When you think about it, we can think of much bigger numbers. We're not going to do so because we don't want to like clutter this board with more numerical points that don't add any more insight from this. But basically, I think you guys see my point. As we come closer to zero, the function values are gonna get larger and larger and larger, and we say that the function tends to infinity as x gets close to zero from this direction. On the other hand, and I'm going to show you a similar line of reasoning. What happens if we're coming in from the left towards zero? As we let the x values get smaller in magnitude, well, basically, you get what I'm saying. -1 over 10, -1 over 100. As the numbers are coming in negative, but closer to zero, what happens? Well, first of all, the numerator is still 1, so the numerator is still positive. We're going to divide by a negative number. So a positive divided by a negative is a negative. And by the same reasoning that we saw here, right, which is, of course, the same kind of reasoning we did here, but with negatives instead, you can see that 1 over x, as x gets closer and closer and closer to zero, will become more and more large negative. So for example, if we were to divide by -1 over a million, if we were to put f of -1 over a million, right, it would be 1 divided by -1 over a million, which would give us -million, right? So the closer we get on this side, the closer we get to zero, we're going to get a smaller and smaller negative number, which when we take the reciprocal of it, we'll get a huger and huger negative number. So we say that the f tends to negative infinity in this case as we approach zero from the left. Okay, and that's why we have this asymptotic behavior with 1 over x near zero. Okay, I hope you all have enjoyed that explanation, and now we will proceed to the trig functions, and yes, it will be a beautiful thing. Yes. You're still there? You're watching this video? Well, I hope you enjoyed it. In any case, if you did enjoy it, well, I encourage you to like it. Put that big thumbs up there. And don't hesitate and don't forget to subscribe to my channel. And anyway, and also add a comment if you want me to cover some particular topic. I can't make any promises. There's a huge list of topics I already want to cover, but time permitting, I may address that topic. And in any case, I hope you've enjoyed this video, and thank you again.